All right, can you see my slide?
See very well.
Yeah, looks great.
Okay. All right. So today, since I'm working on the experimental parts, so today I'm going to like briefly introduce something related with the synthesis and processing of the alloy materials based on what we have been working on for a long time, mostly on the thermoelectrics. But most of these techniques will be used for our high entropy alloy projects. So at the beginning, I'll quickly show you guys some like what we are mainly doing in our thermal lab at Stato building, and following by the synthesis of the alloy materials, mostly covering the powder and alloy ingot preparation methods. And then for the third part, I briefly introduce like the processing methods, mostly for the sintering that we used in our thermal lab for the preparation of the alloy materials. So, so in our lab, we actually have couple labs located at the different buildings at Penn State. So we have the piezoelectric research group at Innovation Park, and we also have the solar and energy harvesting research group at EEL building. And our thermal lab at Stato building is mostly focused on the energy harvesting of the waste heat energy, because as we know that more than 2/3 of the energies is wasted nowadays as heat and exposed to the atmosphere directly. And based on the technical work potential that so all this wasted heat is can be divided into the low temperature grade with about 20%, and the intermediate temperature range with about 24%, and more than half of this waste heat is larger than 300 degrees C. We can normally define as a higher temperature waste heat energy harvesting, and our goal is to harvest those waste heat energy and transfer it into the useful electricities. So now we are we're basically covering the three different aspects for the waste heat energy harvesting, and our major focus is still the thermoelectrics, that we want to cover both from low to medium and high temperature applications using the different types of the thermoelectric materials. And now also recently, we also explored some of the shape memory alloys, utilizing the transition between the martensite and austenite phase to generate the electricities. And also we did some preliminary research on the thermomagnetic generators. As you can see from this figure, this is like basically the this is a gadolinium ring that we can utilize the phase transition between the paramagnetic and ferromagnetic using basically the hot water at the bottom, like to make the torch and make it rotating continuously and generate the electricities. And this SMA and thermomagnetic generators are mostly, we are focusing on the low grade waste heat energy applications. And for the thermoelectric, we are covering the whole temperature range from room temperature to, let's see, 700 degrees C. And speaking of the thermoelectrics, there are two types of the applications based on thermoelectric principle. One is we can utilize the Seebeck effect, which means when a voltage can be generated when there's a temperature difference on the both sides of the conductive materials. So in that case, we created the temperature gradient, then we can generate the electricities. And another one is called the PTR effect that when the current is applied on the conductive materials, then there's there's a heat different temperature gradient can be generated. So this make it possible for to utilize the thermoelectric techniques uh, for the cooling purpose as one solution of the heat thermal management. So nowadays we can basically see some even commercial products like this tiny refrigerator that we used in our car, because this uh, based on thermoelectric techniques, these are solid and no moving part and can make it really tiny and quiet. Uh, so from the materials perspective, uh, the key the key factor is we call it the ZT, which is a figure of the merit, because the conversion efficiency of the thermoelectric devices is directly related to the ZT of the materials as well as a temperature difference. But so the major challenge nowadays is uh, how to improve these individual parameters, including the seeback coefficient, electrical conductivity, thermal conductivity, and because these parameters are correlated with each other, if you try to like change one parameters by, for example, by doping, then the other two parameters are uh, changed automatically in the reverse way. So the major challenge in terms of the materials uh, perspective is how to uh, decouple these parameters and improve the ZT. And for the conversion efficiency of the thermoelectric module and devices, it is determined by the average ZT of the materials at a certain temperature range, as well as the temperature difference that we can apply on the both side, on the hot and cold side of the devices. So this is a schematic figure of how the thermoelectric devices looks like. That normally we connect both N and P type thermoelectric materials electrically in series and thermally in parallel. And so we know people normally started from this couple with only one pair of N and P, and generally we can make it a large scale. So nowadays, the state of the art of high temperature thermoelectric generators is up to only 8 pairs. But in our lab, we have developed large scale, like up to 72 couples thermoelectric modules that I will briefly show in the next few slides. So in our lab, we are mainly focus on the 4 types of the thermoelectric material systems, like the bismuth toloid. Mostly is targeted for the temperature below 250 degrees C applications, which covering both power generation and cooling purpose. And for the medium temperature range up to 500 degrees C, we had the scardite and germanium toloid materials. And like the scardite, it shows very good and performance for the N-type, and germanium it has a big advantage for the P-type materials. And for the higher temperature range up to like 7 or 750 degrees C, we have this rising star of the half-Husler materials, which shows excellent ZT performance as well as a good mechanical properties. So for the medium and to high temperature thermoelectric materials, yeah, we are only focused on the power generations. And this is the power generation efficiency against the heat source temperature of the Carnot efficiency. So as we can see, with increase of the average ZT of the materials, we can step by step increase the conversion efficiency and make it close to the limit of the Carnot efficiency. So nowadays, we are basically about in that range with a temperature difference between 5 to 600 degrees C with a conversion efficiency between 10 to 15%, depends on the if it's like single layer or segmented or cascaded devices. So as compared to the traditional techniques, there are still like a far from the real application of the thermoelectrics that we have to work on both materials and the device design. And so when we moved to Penn State in 2018, we have an open lab, and nowadays we have this like fully equipped in-house streamline covering from the material synthesis and the characterization to the module fabrication and testing. So we can fabricate from unit couple to the large scale of the module and measure power and conversion efficiency in our lab. And also in terms of the applications, we are covering both the body heat energy harvesting and cooling, the wireless sensor nodes in the smart buildings, and the thermal refrigeration and air conditioner. These are some examples that we have demonstrated in our lab based on the different types of the thermoelectric materials. So far we have made a lot of achievements. Like we have really improved the ZT of the different types, like half-Whistler and bismuth toloid materials, for the with the excellent ZT as compared to the state-of-the-art results. And also we made the different scale of the thermoelectric modules, and with has improved the conversion efficiency from about 6% to 12% that we have published so far. And on the other hand, so the oxidation resistance of the thermoelectric module is another concern for the high temperature energy harvesting. Through the materials compositional design and brazing techniques. So this is one result that we have shown the less than 10% degradation of the device after 7 days operated directly in the air without any inert atmosphere or the oxidation resistance coating protection. So this is a very good way to show that even without the thermoelectric materials and the device itself can has improved the oxidation resistance. And this is the 72 couples half-Whistler module we have fabricated in our lab, which provided the record high power total power output larger than 55 watts under the temperature gradient about 570 degrees C. Okay, so these are basically a brief introduction about what we are doing in our lab and we have achieved so far. And in the following slides, I will briefly show the techniques about focusing on the synthesis and processing of the alloy materials that we use for the thermoelectrics, which can also be applied for the high entropy alloys. So the first most widely used method for the alloy material synthesis and preparation is a high energy ball milling. This is a schematic diagram show how it works. This is not the traditional plenary ball milling. That's the ball and the jar will only rotate one dimensionally, like in a plenary. So this is high energy ball milling can provide the 8 motions with the ball milling jar and make them much more contact and generated more heat between the balls and the materials. So it breaks the raw materials, and then this high energy the high energy ball milling can generate the heat when the materials contact with the balls. So for some of the alloy materials, it can directly form the desired phases, which is also called a mechanical alloy. But for most of the alloy materials, this technique is to provide to generate the nano powders, which can be further uh, fabricate or synthesize the single purity phase or any desired phase of the alloy materials. So the uniformity and the how good we can prepare the materials, alloy materials using high energy ball milling, it depends on the ball milling jar. Like for some sensitive materials, we don't want to really to use a stainless steel ball milling jar. Instead, we prefer to use like tungsten carbide or zirconium based ball milling jar to avoid any cross contaminations. And the nanoparticle nano size and distribution is basically determined by the mass ratio between the raw materials and the balls, and also the ball size. And basically, we can either do it using like some grinding solutions, like the toluene, or basically we just do the dry ball milling, which applies for the alloy materials, which is sensitive to any liquid medium. So this is one example of the half-Whistler materials we prepared in our lab. So this figure shows the hand-grounded not powders from the ingot. This is a ball milling. We can see the particle size is much smaller and uniform, obtained from the high-energy ball milling. And this is example how fine the particle it is. So it's by accident when the first time some nanoparticles drops off and exposed in the air when we load it into graphite die for the SPS. Then it led to this exposure in the air in like 1 or 2 seconds. 1 or 2 seconds lead to the self-ignition of the particles due to the oxidation of these nanoparticles based from their very large surface areas. And this XRD figure shows how the diffraction pattern changes with the increasing of the ball milling time. As you can see, the diffraction peak is getting broader and broader, indicates the particle size of the nanopowders is decreasing with increase of the ball milling time from like 100 nanometers to about 20 nanometers. And another commonly used synthesized method for the alloy materials is induction heating, which is basically is a process of the heating for the electrically conductive object through through the heating inside the materials by the magneto induction. So this is a setup that we have inside the building with a heating coil surrounding the cost tube, and we put the materials in the different the crucibles inside, and by steply gradually increase the current, we can get this molten metal homogeneous under the argon atmosphere. This is the picture of how ingot looks like. But normally, in order to achieve the homogeneous ingot, we just repeat this heating and cooling couple times. And based on the object size and how good the connectivity of the materials and how the coupling between the induction heating and the materials, also the penetration depths, we need to we need to determine how high the frequency of the electrical current that we want to use. Yeah, so also in our when we prepare these half-Whistler materials using the induction heating, we also find out that how uniform or the single purity phase you can achieve is also related with what types of the crucibles that be used. like when we use only the graphite, we load the raw materials in the graphite crucible without any lid covered on the top. We have this really lot of annoying impurity phases. With the lid on the top, we can get mostly the half-way desired phase, but still we cannot avoid the impurities. Then we tried like use another crucibles inside the graphite boat. We tried both the tungsten and alumina. Then it shows this combination of the graphite and tungsten provides the best results for the induction melting of this desired half-way phases. So this induction melting basically it can provide rapid heating with a high temperature. So in the lab normally we can this induction heating can provide the melting temperature about 2,000 to 3,000 degrees C, and with the proper selection of the crucibles, we can get rid of the contamination and achieve the uniform phases. So for the high energy ball melting and the induction melting, we normally just leave it cools down naturally, but for some of the alloy materials, we want to maintain the phases only existed at high temperature. This is one example of the scatterized thermoelectric materials that the desired phases is cobalt antimony 3 phases, which only exist above 1100 degrees C. And if we use either ball milling or induction melting and just let it cool down, then we can only get multiple phases, including all these secondary phases, and even with the post-annealing, we cannot achieve the single purity phase. But by applying the quenching process, which can provide much faster cooling rate, then we can basically overcome these secondary phases and achieve this only desired cobalt antimony 3 the major phase as we desired. And of course, we still have, because the cooling rate maybe still not high enough, so we still get these secondary phases, but which can be we can remove it by the post annealing to achieve the single purity phase. So based on this quenching principle, we also in our lab we also modified our induction melting a little bit. So this is how it looks like originally, that we hold the crucible using the refractor brick, and with a new design that we hang the crucibles with the wires and locate it at the heating region. And right after the heating is finished, we just lower it down and make it conduct with the copper block at the bottom directly, where the copper block is cooled by the circulating water. So in that way, we can provide the faster cooling rate for the materials that we prepared by the induction melting. But still, this is the contact area between the crucible and this copper block is limited. So the cooling rate we can provide by even this method is still limited. Then for those kind of the materials, we have another two basically different techniques for the preparation. One is called vacuum melting water quenching process. So basically, we load the raw materials into the quartz tube and seal it under the vacuum. When we have some materials which are potentially reactive with the quartz, then we can prepare this graphite coating inside the quartz tube, which so basically we wash the quartz tube, for example, with ethanol, and like dry it a little bit, kind of like a dip, then heat it with oxyacetylene torch and make this ethanol layer inside quartz tube change to the graphite to protect to provide a protection layer between the raw materials and the quartz tube, and vacuum seal it. Then just basically heat it up in the morpho furnace and get it melting. Then we do the water quenching. So at the high temperature, like this is about 1100 degrees C, then we take it out and quickly drop it into the water, and then it can cool your materials down from 1000 degrees C to room temperature, like in couple seconds. So this is how the ingot looks like prepared by this method. And so when we were dealing with p-type scar materials, since there are a lot of iron, it's a lot of iron content compositions. So even with this graphite coating, sometimes we still have these crack issues due to the reaction between the materials and the cross tube. In that case, we can put additional graphite tubes inside the cross tube and reload the materials inside the graphite tubes to further avoid this reaction between the tubes and the materials using this method. So there are also some commercially available this quenching furnace that they basically either connect the cross tube with like a rod with either mechanically or magnetically, and like just drop it to the bottom water tank right after the heating. But those are much more expensive than what we can do in our lab in current way. But the only limitation from this method is that limited by the quartz that we used. So the melting temperature is limited by maybe around 1300 degrees C, because for this method we can only heat it up slowly, so we cannot really keep the cross tube above 1300 degrees C for a very long time. In that case, there's another method called arc melting to provide much higher melting temperature together with a quenching process. This is how it looks like. So the raw materials is heated by the eddy current generated between the tungsten electrode and the raw materials located in the crucible inside the copper hearth. And the copper hearth is actually can be cooled by the circulating water. So right after the melting is finished, we just turn on the circulating water. So this provides also the very fast cooling rate in order to get the compositions that we desired only exist in a high temperature. And this arc melting method is also the most widely applied method to prepare the high entropy alloy nowadays. And there's another method called spin melting, which can provide even faster cooling rate. So basically, we load the raw materials inside the crucible, which is made either by quartz or like boron nitride, and we heat it up like what induction melting did. So after the metal is fully melted, and due to the relative higher viscosity, it will not come out from the hole at the bottom. Then at the third ejection stage, we apply the inert gas pressure and press out all the molten liquid and let it drop on the high-speed cooled copper wheels, and then to produce the ribbon type of the materials. So in principle, this spin melting can provide a high cooling rate up to 10 power of 5 Kelvin per second, which can produce kind of the amorphous alloy materials that can benefit the further nanostructure and nano engineering of the backlit materials. But also this method has kind of the temperature limitation based on how the crucibles are designed and how reactive of the materials used, which can be inducted with by the induction melting method. So this is video of how it looks like. So we have the bismuth toloid materials inside and get it melted and press it out using the inert atmosphere and drops on this high-speed copper wheel cooled by the circulating water. So this is so how the ribbon materials can be fabricated depends on the couple parameters, including the nozzle diameter, and the temperature is basically controlled by how large current you want to apply, and the gas pressure, the distance between the crucible and the wheel speed. So this is one good example and one bad example how when you modify those parameters. This is good one that you can get the nice and narrow ribbons. This is bad one. Something goes wrong, you get fully like piece of like chunk type of the materials that which is not that too good for the spin melting. So yeah, for most of the materials, in order to get more homogeneous compositions, that we requires the post annealing. So we can either do it under the vacuum. This is what I mentioned earlier, that for the vacuum purpose, we seal it in the cross tubes, or we do it under the inert atmosphere using the tube furnace to get a single pure and uniform phase. And besides the phase perspective, we can also control or modify the microstructure, such as the defects, grains, grain boundaries, and the porosity of the materials through the post-annealing process in order to match what we desired for the applications. And then for the processing of the alloy materials, in our lab, we basically use two methods. One is spark plasma sintering. Maybe most of you are familiar with this method. That's the current, as compared to the conventional sintering method. For the SPS, the current can go through both the materials itself and the graphite dies surround the materials. In that case, we can provide really high heating rate in order to maintain the intrinsic properties of the materials, like the nanostructures. And we basically have two SPS setups. One is located at a statue building. This is like a home customized, like open system. We don't really require the like vacuum chamber. We just seal the materials using the tight graphite dies. And we have some like air sensitive alloy materials, and we never had an issue with any potential oxidation issues using this equipment. And this one, since we don't need the high vacuum chamber, so this is really good for the high throughput synthesis of the sintering to like every 15 to 20 minutes, we can finish one round and load another one to start. This is another commercial SPS we had at Research West nowadays. This from Japan and has a huge vacuum chamber. This for more really more air sensitive samples and for some experimental testing, that when we have some new ideas. So this one, because you need to vacuum and purge and vent every time, so it takes much longer, 1 to 2 hours for one sintering. So this is one example of how the SPS as compared to the traditional sintering method, that with a high cooling heating rate, we can finish the sintering in couple minutes. And in that case, through the diffusion promoted densification, and we can maintain the intrinsic properties of the nanopowders, which is important to improve for the improvement of the mechanical properties of the alloy materials. And this is one how it looks like for during the SPS sintering. The particles connected neck by neck at the beginning, and with this diffusion promoted densification, it shows like then the particles, close particle connect to each other at the end, make the fully dense bulk materials. And also for the SPS, we can basically fabricate the desired shape, even it's like complicated, because all this graphite tools can be processed very easily and machined with even the complex shapes. And another processing method for the synchronous.
Wenjie, I want to ask you, how many more slides do you have?
I have only 2.
Okay, great, thank you.
Yeah. So it's hot extrusion. This is an industrial example of how it looks like. We heat the materials inside and press it through the die with the specific shape that we want. This is example of the steel steel box produced by the hot extrusion in the industry. But in our lab, we have this extrusion at Research West. So what we are more interested in is using this hot extrusion method to texturing the certain type of thermoelectrics materials. One example is bismuth toloid, which basically has a trigonal structure, not a cubic. So it shows an isotropic thermoelectric properties in plane and out of plane. So the texturing is really required to improve the high ZT. This is example because for the SPS generally just produce mostly random grained materials as shown in this figure, but through the hot extrusion, we can really get the very good textured materials that we can improve the ZT by 20 to 30%. And another, not only like this type of the extrusion, people are also trying the different types of the extrusion, like this one, because they want to like generate more defects or like the dislocations type of things inside the thermoelectric materials as a additional phonon scattering source to lower the thermal conductivity. Yeah, this is the last slide that we prepared the bismuth toloid ingot in our lab with different dimensions. So this is a schematic diagram. So basically, in this region, we have really nice textured materials with a layered structure, which can show the much better thermoelectric performance. Yeah, I will end up here.
Okay, thank you.